Okay, question 4 of the thermodynamics tutorial. Okay, so we are given a series of disproportionation reaction, so in which you can see that all the monoxide, right, so for example carbon, is disproportionation, undergoes both reduction and oxidation simultaneously. Okay, so you have the series of group 14 elements undergoing disproportionation reaction, and you are given the delta S, delta H, and delta G. Okay, so the first question asks you for the entropy change, which is the delta S. Y of that for SiO is much larger than that of CO. So you can take a look at the two entropy values. The entropy values for SiO, it's a lot more negative as compared to the carbon monoxide. Okay, so if you take a close look at this, we just largely be due to the number of moles of gas change. So it's a reaction. So we focus on the number of moles of gas. Before reaction, for both of them, right, you have 2 moles of gas. But for the carbon monoxide reaction, you have 1 mole of gas at the end of it. Whereas for the silicon, you have 0 moles of gas. So both of them, both reactions, have a negative entropy change. There's a decrease in entropy. Alright, but the decrease in entropy for the second reaction, alright, it's a lot more because it's from 2 moles to 0 moles of gas. Okay, so that will frame our answer for part A. For part A, first of all, explain why is there a decrease in entropy because of the decrease in number of moles of gaseous particle for both the reactions. Then organize your answer to highlight the difference. The difference will be then for SiO, the decrease is from 2 moles to 0 moles, whereas for CO is from 2 moles to 1 mole. And therefore, notice the term that I use, the delta S entropy change, we don't use larger, smaller. Again, as I mentioned in thermodynamics, because of the sign, we use the term more negative or more positive. Alright, so in this case, this value here is a lot more negative compared to that for CO. Okay, that's for question 4A. Okay, for 4B, we are supposed to suggest an entropy change for the disproportionation of germanium oxide. So germanium oxide is here. You can see that this is blank here, waiting for us to fill up. And using this value, we're supposed to calculate the delta G of this reaction. Okay, so if you take a look at this reaction, there's of course various ways to compare to get a value. One way is to look at the comparable reactions. So for germanium oxide, you have solid as the start. So naturally, I will not compare with the first 2 reactions. Why? Because the first 2 reactions are gaseous. Okay, then we take a look at the products. The products are solid for germanium oxide, tin oxide, and lead oxide. Okay, so you can see that these 3 sets of reactions are very comparable. And therefore, these 2 values here could give you some guide in terms of what the entropy change should be. So one look at these 2 values, you can see that these 2 values are highly close to 0. Because the reaction does not involve any physical state change, right? And no gases are produced nor used up in this reaction. So the trend between tin oxide and lead oxide, so if you guys look at your periodic table, germanium, then followed by tin, and then followed by lead, they are all in group 14. So the difference between tin and lead, it's about 5.2 J per mole per Kelvin. Alright, J per Kelvin per mole. So expectedly, this difference will also be about 5.2. So to propose a value, to make an intelligent guess, I can propose negative 14.4 J per Kelvin per mole. Okay, so that's what I do over here. Okay, again, the basis is that I look at the difference in value. The difference in value is about approximately 5.2 J per Kelvin per mole. So once I have this value, I can use this value, this delta S value that I have, substitute into here, this equation, to find my delta G. So since I'm given the delta H, okay, I can substitute in delta H of negative 126.8 kJ per mole. So in this case, because we are finding delta G, the delta G units in kJ per mole, the delta H units is also in kJ per mole. It makes sense, since we are finding delta G, to convert delta S into kJ per mole per Kelvin. Okay, this will ensure that your units are consistent. So take a look, delta G, delta H are in kJ, delta S is in J, so we need to divide by 1000 to convert J to kJ. Sub in your values for delta H. Temperature will be at 298 Kelvin, as mentioned in the question. Correct your answer to 4SF. Okay, so since we are supposed to calculate delta G, typically the SI units for delta G will be in kJ per mole. Okay, kJ per mole. Okay, alternative for this reaction, because you may look at this reaction that it's a solid to solid to solid, some of you may be tempted to assume that the delta S is 0. Alright, this is also possible. Okay, because there's no negligible entropy change. Okay, with that, we'll move on to 4C. Okay, for 4C, basically we are looking at the reaction of the carbon monoxide. So if you take a look at carbon monoxide, the delta G is negative. So quick recall, delta G less than 0, reaction is spontaneous. Delta G more than 0, alright, not spontaneous. So we're supposed to calculate temperature above which the disproportion of CO would not be favorable, which means in this case, the reaction is unfeasible, which means we're looking at the temperature in which delta G is going to be more than 0. Okay, so we can make use of this equation, delta G equals delta H minus T delta S. Now, it's very evident that we're looking at the temperature term. So earlier on, in the case for carbon monoxide, we have the values of delta S and delta H. So if we make a simple assumption that the delta H and delta S do not vary with temperature, we can substitute in these values. Set delta G to be more than 0. So over here, I get the value of negative 172.5 from earlier part. Okay, delta H, and then delta S, negative 175.9. But over here, recall, I need to convert delta S into kJ per mole per Kelvin, because your delta H is in kJ per mole. And now we want to find delta G. We need to set delta G to be in terms of more than 0. So again, it's like we are finding delta G. So it makes sense for us to convert your delta S into kJ per mole per Kelvin. Once you have that, solve for your T, you get T to be 981. So which means at temperature above 981, this reaction is no longer feasible. So in this case, the reaction we are looking at is 2CO to form C plus CO2. What we are saying is that above 981 Kelvin, the forward reaction becomes not favorable. Okay, it also means that at above 981 Kelvin, the reverse reaction therefore becomes favorable. Because if the forward is not feasible, the reverse reaction will become feasible. So beyond this temperature, delta G will be more than 0. In other words, the reaction would reverse in direction. Okay? That's 4C part 1. Last part for 4C is to look at why, although we calculate the delta G to be more than 0, right? So at 298 Kelvin 1 bar, we look at the question. The delta G naught is negative 120.1. Okay, so it's given in the question, delta G naught equals to negative 120.1 kJ per mole. So technically, delta G naught is less than 0. By right, the reaction should be spontaneous. So why didn't we see it happening? So again, in this case, because the question gives you standard condition, so it matches the not sign. Not sign is 298 Kelvin, 1 bar, right? That's the standard condition. So the only possible reason is that in thermodynamics, we only account for the thermodynamically feasibility. We do not take into account the kinetic feasibility. What do we mean by kinetic feasibility? Alright, we're looking at the concept of your activation energy and the rate of reaction. So some reactions may be thermodynamically feasible, but because it's too slow due to a very high EA, it becomes unobservable. Okay, so a classic example that I can think of will be the conversion of, so if this is energy, your diamond and your graphite. Technically, graphite it's more stable as compared to your diamond. So logically, based on thermodynamics consideration, we should see diamond converting to graphite. But do we see that happening in real life? Alright, we don't, because why? Your activation energy, it's very, very high. Alright, so the EA is very, very high, which means, alright, your EA, this portion of the EA, right, is very, very high, which means your conversion of diamond to graphite will not happen in a lifetime. And that's why the marketing, right, diamonds are forever, right? Okay, because the conversion is just extremely slow. Okay, but who knows, maybe if you supply some heat, right, it may accelerate the process. So anybody game to burn some diamond? Okay, if not, we move on to the last part, 4D. Okay, the 4D we're supposed to calculate, or rather not supposed to calculate, we're supposed to comment qualitatively. Now, when this term qualitatively appears in the question, basically means no calculations. Alright, we're looking at this reaction. I've taken the liberty to repeat the data over here. So basically, we are supposed to comment on the entropy, enthalpy change, on the feasibility of the reaction. So for feasibility of reaction, basically we're looking at delta G. Whether is it more than 0 or less than 0. So largely, we're considering delta G at two different scenarios. Either low temperature as well as at high temperature. Okay. So this is what I mentioned. Delta G more than 0. Non-spontaneous. Delta G less than 0 is spontaneous. So we're going to make use of this equation. Delta G equals to delta H minus T delta S. I'm going to make a slight modification to this equation. Mathematically, it's the same. I just consider instead of a plus, instead of minus, I put a plus and then I put negative T delta S like this. Okay. What's the purpose of doing this? It's so that I can see delta G as a cumulated effect of delta H as well as negative T delta S. Okay, it's easier to consider addition terms as compared to a subtraction term. So which means to predict the sign of delta G, to think of it whether it's more than 0 or less than 0, I first have to consider delta H and then negative T delta S. Okay, so in this case, delta H is given, it's positive. Delta S is negative, so delta S is negative, which means negative T delta S, because temperature is in Kelvin. Kelvin can only be positive number, so negative of a positive number, so it's negative. Negative multiplied by a negative term, you end up with a positive term. So in this case, you have a positive delta H term, you have a positive negative T delta S term. When you sum these two terms up together, it will always be positive. Which means, conclusion is that delta G will always be more than 0. And this happens for all temperature. okay, for all temperature. Okay, so which means, in other words, it will be non-spontaneous for all temperature. Okay, so take a look at how we present answers. So state first the sign of the delta H, sign of delta S. Explain the effect on negative T delta S. So if both of them are positive, which means delta G will be more than 0 for all temperatures. And therefore, the reaction is going to be non-spontaneous at all temperature. Okay, with that, we are done with all the questions in question 4. Before you move on to the next question, I just have a review question for you. Can we try to do one more similar question to D, which is E? Alright, you may pause the video. Basically, what I want you guys to do is to look at this reaction of tin oxide to form tin and tin dioxide. Use the same analysis and conclude on the feasibility of the reaction. Okay, you can pause this video now to try this question. When you're ready to resume, you can play the play button. We'll go on to the explanation. Okay, so let's take a look. We employ the same concept. Delta G naught equals to delta H naught minus T. Rather, to be more exact, do like what I did earlier on. Right? Consider plus negative T delta S. So in this case, the values given for delta H is negative. The value given for delta S is negative. As a result, negative T delta S will be a positive value. Now, clearly, this is very different from the earlier example. The earlier example, both delta H and negative T delta S are positive. But in this case, delta H is negative, but negative T delta S is positive. Which means there are possibilities in which your delta G can be both negative, can be negative as well as positive. So when does it become positive? So there are two scenarios, right? Delta G can now be more than 0, or delta G can be less than 0. So when can it be more than 0? If it's more than 0, it must mean that this positive term must outweigh the negative term, which means this happens when negative T delta S, the magnitude of negative T delta S, must be bigger than your delta H term. Okay? Delta G will become negative when your delta H term, which is negative, magnitude is bigger than your negative T delta S. Okay? So just let me rearrange this. We have positive over here. So with that, if you take a closer look at this question, when can the negative T delta S magnitude be bigger than that of delta H? Okay, when your temperature is, how do you have a higher magnitude? When the temperature is high. On this other hand, we want the magnitude of negative T delta S to be small, so when temperature is low. So delta G more than 0, it's going to be non-spontaneous, which means the reaction will be non-spontaneous when temperature is high, and the reaction will be spontaneous when temperature is low. Okay, and that's what we're going to write in our answer here. So given both delta H and delta S are negative, similar, so state the sign of your delta H and delta S immediately. Focus the attention on negative T delta S. Alright, so at low temperature, your T delta S, okay, let me just make a modification over here. Let's just change this to negative T delta S modulus. Okay, we are interested just in the magnitude, so negative T delta S modulus is smaller than your delta H because the T term is small. So as a result, your delta G will be less than 0. Okay, which means this is going to be a feasible reaction. At high temperature, your T delta S term, okay, same thing, just let me incorporate the negative sign inside. Okay, your modulus of negative T delta S will be greater than your delta H, and as a result, your delta G is more than 0 at high temperature. The reaction is going to be spontaneous at low temperature and not spontaneous at high temperature. Okay, that's it for question 4.